Let's apply everything we've learned about differentiation so far. So in this question, we would have been described some sort of water tank where its length is 3 times its base and it has some height. We're told that the surface area of this tank is 12 meters squared. We need to find the maximum volume of this tank. Okay, so we'd need to read the question very carefully because sometimes these tanks have lids on them and sometimes they don't. Let's assume in this case that our water tank does not have any upper surface, so it doesn't have a lid on top of the tank. If that were the case, so this surface here does not exist, how would we find its surface area? Well, we'd need to consider all of the faces on this tank. So let's just draw in those missing surfaces. So we know that the surface area, let's call it A for area, is 12. And we want to find the maximum volume. So we'll call it V max. Okay, we want to find that maximum volume. Well, that appears to be hard because usually we would just differentiate volume. That's how we find maximum points, and we want the maximum point on this. But let's have a look at the formula for volume we would have. We'd have to do length times width times height. That's going to give us 3x squared y. Problem. We don't know how to differentiate stuff with x's and y's in it at AS, so we're going to need an alternative approach. We need to get rid of either the x or the y from this formula. Well, they've told us something about the surface area, so that seems a good place to start. Can we write down the surface area in terms of x and y? Well, let's see. We've got this bottom surface. That's going to be 3x squared, the base. There is no lid, so we'll only have one of those surfaces. Then there's also going to be this face here. That's going to be xy. We'll have another one of those over the other side, so we'll have 2 lots of xy. Similarly, we're going to have this big front face here. That's going to give us 3 lots of xy, but we'll have another one of those around the back as well, so we need to double that. We have 6xy. So what does that tell us? That tells us that this total surface area, which we know is 12, could also be written as 3x squared plus 8xy. Now we notice we have an expression for x and y. We can make y the subject of this formula and then substitute it into here. So let's do that. Looking at this, we can say 12 minus 3x squared is equal to 8xy. Dividing through by the 8x gives us 12 minus 3x squared over 8x is equal to y. That's perfect. We can now take this value of y and substitute it in here. So we're using our knowledge of simultaneous equations here to eliminate a variable. The volume is equal to 3x squared multiplied by 12 minus 3x squared all over 8x. Simplifying this down is going to give us one of those x's cancels with that. Expanding the brackets gives us 36x squared minus 9x to the 4. Sorry, I forgot that I should have cancelled one of those. So we just have 36x minus 9x cubed, and both of those will be divided by 8. That will give us a formula for volume. We can simplify that a little bit more. Both of those divide by 4, so we get 9 over 2x minus 9 over 8x cubed. We have a formula for volume which is now only in terms of x. This means we can differentiate it. Again, we knew we wanted to differentiate. It spoke about a maximum point, and we've just seen in previous videos that differentiation can tell us about maxima. Okay, so let's continue with that. We now need to find the derivative of v with respect to x. So notice I'm not writing dy dx anymore, simply because I'm not differentiating y with respect to x. I'm differentiating v with respect to x. So times by the power, reduce the power by 1, times by the power, reduce the power by 1. We're looking for stationary points, so we know that that derivative must equal 0. Make sure you state that in the exam. That will get you a method mark. Okay, now we need to do is solve this. So let's multiply through by 8, because that will remove our fractions, and we're going to get 36 minus 27x squared is equal to 0. And then we can just have 36 is equal to 27x squared. Dividing through by the 27 gives us, that's going to be 4 over 3. I'll just double check that. There we go. Is equal to x squared. Therefore, x is equal to plus or minus. Remember, whenever you take a square root, you do get two solutions. 2 over root 3. Or, to write it a bit nicer, plus or minus 2 root 3 over 3, a rationalised denominator. Okay, we know that we can ignore the negative root here because x represents a length. We cannot have a negative length, so let's just give ourselves a little bit more space. X is 2 root 3 over 3. Some people think they're now done, but that is the x-coordinate. We were asked for the maximum volume of the tank. So we just need to plug that x value back into our formula for volume. 9 over 2 . So let's just put that in the calculator. That gives us a maximum volume of 2 root 3. So that is the largest possible volume I can have for this tank. How do we know it's a maximum? Well, sometimes these questions will ask you to justify that it's a maximum point. Remember, we can justify it's a maximum by looking at the second derivative. Differentiating this again will give us constants go to 0, times by the power. Again, try to cancel fractions when you can, rather than doing 54 divided by 8. Just less calculation, less prone to error. We know that x is 2 root 3 over 3. Cancelling a factor, cancelling another factor. That gives us 9 over 2 root 3, which is, I forgot my negative. I was about to say which is greater than 0, therefore we have a minimum. That let me know I had an error in my calculation because it wasn't what I was expecting. I look back, spot my error, and correct it. Now I can say that is less than 0, therefore v is a maximum. V is maximal. Okay, so that's our method. Take the second derivative, show that it's less than 0 and therefore a maximum. If you make an error, have a look through. There, I knew I had the wrong sign, so I had a quick check to see if I had a sign error. I spotted it, I fixed it, I didn't waste any time. That's how we can solve applied problems. Quick summary. Write down the information, draw a sketch. We will be told something about one of the dimensions, either surface area or volume, length, something. We write down the area and a formula for the area. We write down the volume and a formula for volume. We notice that this has two variables, therefore we need to eliminate one. In this case here, we made y the subject, and therefore we could eliminate y. Often in the question it will be a show that, so you know which variable should be eliminated. We substituted it in, we simplified, continued to simplify until we had a nice formula for the volume in terms of just one variable. Once we had a formula in terms of just one variable, we could differentiate, set to 0 because we're looking for a stationary point, solve, ignore any solutions which don't make sense in the context of the problem, and then substitute that value of x in to find our volume. We justify that our volume is a maximum by looking at the second derivative. The second derivative is less than 0, therefore we know it's a maximum. And that's the entire process for applying differentiation to these contextualized problems.